Another controller choice we have is using an integral control. So continuing from the previous example, we saw that proportional controller did not work. We could not get a steady state value of our output of the desired 5 volts. Again, it is going to be specific to the plant or the open loop system we're working. So another option would be to use an integral control. Again, I'll caution this will not work for every system either, but it's something we can try, and mathematically we can show before we try to implement it, is it going to work or not to achieve everything that we want. So the integral control, instead of simply taking the error, the difference between the reference signal and our actual signal, what we're going to do is we're going to integrate our error or sum our error over time. So really what we're doing is we're finding what's the area under the error curve when we're using an integral controller. Again, sometimes we're going to be higher than the reference, sometimes we'll be lower. So these positive and negative areas over time potentially will cancel out and we'll be left with 0 once we've achieved our steady state value. So the error itself must go to 0 for the integral to eventually go to 0, because otherwise we're going to keep adding value or keep subtracting value to it. So for some systems, and we'll see in this one it does work, in some systems it's able to drive our error to 0 or achieve the desired constant value for our steady state response. We saw in the previous, using a proportional controller, the closed loop system and the open loop system or the plant had the same order. They were both first order systems for this case. That's not going to be the case when we put an integral controller. It's actually going to change the order of our closed loop system, which can be a good thing because it gives us some options of how we want to design the controller to get a desired response. And we'll go through that for, again, this same plant. It's the same plant as before. We want to control this RC circuit, this 1 over 2.5 S plus 1. We still want its constant steady state value to be 5 volts, and we want to be able to get to that 5 volts quickly. So this is going to be the schematic for our closed loop controller now. So we see in that dashed yellow or orange box, we are going to still get to choose this gain. I'm calling it case of I now because it's an integral gain. And we'll see when we get to more advanced control systems where we put together different types of controllers, we might have multiple gains we can choose. So what's happening is that this, I'm taking the error, I'm passing it through my gain, and the gain can be achieved just through some op-amp circuit like we've seen before. We are going to be amplifying our signal. So that's what this controller is really made up of. For the proportional controller, it would just be that op-amp that's just doing some sort of amplification of the signal. But now we're going to amplify the signal and we're going to pass it through this 1 over S block. As we know from Laplace transform, a 1 over S is integration. So this thing in yellow that we're designing would be some circuit, if we're doing in hardware, it would be some circuit we build that has this amplification and a 1 over S term to it, or we could do this in software in different ways. Right? But effectively, we're going to be multiplying the error by this 1 over S and by our amplification. That becomes the input into our plant, and then that goes through the plant and becomes our output. So general idea is still the same as the previous problem. It's just that the controller we're using is just a little bit more sophisticated, and we're going to choose this Ki. So let's go through the same process we did for the proportional controller. Is we really want to see, because we're putting this plant surrounding it by this feedback loop, we're trying to see, well, what's the response of E out over the reference signal? Reference signal is unchanged. It's what we want the output to look like, that 5 volt step function. We're not going to get there, again, in the ideal manner, but we want the steady state output to be 5 volts. So we use the same rules as before. We're going to multiply our controller, which is now Ki over S, times G out. And it's this feedback loop, this negative feedback loop. So now we have Ki over SGO over Ki SGO plus 1. Okay? And in the previous proportional, it was just Kg over Kg plus 1. But now we have that 1 over S term that's built into our controller. So if we go through the algebra, we clean it up and we put it in descending powers of S like we want to do. Now our closed loop transfer function is this ki over 2.5s squared plus s plus ki. All right, so what happened between the plant, which was first order, now when we put this integral control in, now our closed loop system is a higher order. It's now second order. And again, we can treat it just like any second order system we've dealt with before. We know how to analyze it. So first, let's see, does this controller work in that? Does it make our error go to 0? Does it make E out eventually go to 5 volts if our reference is 5 volts? So using final value theorem on now this closed loop transfer function, the E out over R, the same steps as before, I can see what happens as s goes to 0 of s E out, and I can take the limit as s goes to 0 now. All right, so I can take this expression with this new closed loop transfer function, and I'll evaluate this when s is 0. So just like before, the s from here is going to cancel that 5 over s, and the 5 on top is going to be combined. And let's see what happens here is I can now evaluate this when s is 0. So the 2.5s squared, that goes away. The s, that goes away. I'm going to be left with a 5 ki over ki. The ki's go away, so I'm left with 5. So the steady state value, or the final value of my output, is now 5. So let's note, how is this different than when we were just using the proportional controller? Well, previously we saw that it was dependent on the value of the gain that we chose. Going back to the proportional controller, we saw again it was 5k over 1 plus k. It depended on what k we chose. For the integral controller, we see we don't have that. It's always 5. It doesn't matter what ki we choose, it's eventually going to get to 5 volts. Now the k does influence how it gets to that 5 volts, which we can look at now. So once again, we have created in the closed loop system this second order system. So it's going to potentially have oscillations, it's going to have a peak time, it's going to have an overshoot that with the proportional controller we didn't see because that was first order. With the open loop system we didn't see, that was first order. But again, this is second order. So putting into that standard form, since we have a second order system, I want that leading coefficient to be 1, so I can divide everything by 2.5. So I'll work with this form of our closed loop transfer function instead. Well, we can look at the poles because those are just the zeros of the denominator. And we can see here what it's going to turn out to be. What we generally want, though, when we're working with controllers, is we generally want our closed loop transfer function to be underdamped. There might be times we want an overdamped or a critically damped system, but most of our analysis will revolve around having underdamped systems. All right, so let's assume right now we're choosing a ki such that we're going to have an underdamped system. Well, that means that this expression inside the square root has to be negative so that the poles are going to be complex conjugates of each other. So if we just look at what's happening here, if we choose a very, very small value of ki, small but positive, we could get the expression in the square root to be positive. We typically don't want that. We'll investigate our choice of ki more in the next lecture. But here, as long as our ki, even if a ki of 1, we're going to get complex conjugates for our poles, which means it's going to be underdamped. But let's see, because ki is involved in this constant term here, therefore it's going to affect the natural frequency of this system. So we know that since we're in standard form, the square root of this constant is going to be our natural frequency. And then looking at that middle term, we know that the middle term, 2/5, is equal to 2 zeta omega n. So also, our choice of ki is going to affect our value of zeta. So the damping ratio and the natural frequency of the closed loop system are affected by the gain that we're going to select. So what does that mean? Well, again, we know from the last unit, looking at second order systems with a step input, that the damping ratio and the natural frequency are going to determine things like the peak time, is going to determine the max overshoot, the settling time. So the response of our system is going to be dependent on that ki that we choose. How fast does it respond? How much does it overshoot? Both are going to be determined by the gain that we choose for our system, as well as what's the input into our system, like we saw in the previous example. So we're going to see, again, through simulation right now, how our choice of Ki is going to affect those aspects. And in future lectures, we're going to look a little bit more analytically up front. How can we determine it without having to rerun these simulations multiple times? So looking at the Simulink for now our integral controller, it looks largely the same. We are going to choose this Ki, this gain that our error is going to go into. So really the only difference is, the only thing I've added is this integrator, this 1 over s term, that is going to determine what the input into our plant or our open loop circuit is going to be. The reference is still the same. We want the output to look like a 5-volt step function ideally, but let's see how the system is going to behave differently with this integral or I controller compared to how it acted with a proportional controller. All right, so let's go through, again, just some example gains. We could choose any positive gain, but let's start with just a gain of 1. What's going to happen to it? So like we saw on the slide, the gain is going to determine some of the parameters of this second order system. So here I'm displaying the natural frequency, the damping ratio, and just the peak time. We could show the max overshoot. We're also going to see that graphically. So when our gain is 1, we have a natural frequency of 0.63 radians per second. We have a damping ratio of 0.32, so it is indeed underdamped. And the peak time is 5.2 seconds. And looking at the graph that's displayed, it looks like a second order response because it is a second order response, but it looks different than what we saw with just the proportional controller. All right, so we see that peak time there around that 5.2 that we saw from the plot. And we see, also importantly, the steady state value of the output is going to be, it's very close to 5, and those oscillations are only going to get smaller. So one, probably the most important thing we're interested in, does the error go to 0? Well, I can also look at the error value, the difference between the reference and the output. Yes, it's very, very small. If we ran this I ran for 30 seconds, we could run it longer. It's only going to get smaller and smaller. If the error goes to 0, that means that the output voltage is approaching 5 volts. So unlike the proportional controller, even at a gain of 1, this did what we wanted. One aspect of what we wanted, the steady state response is 5 volts. Let's also look at the input voltage, which we can't really see. We're only first seeing now in simulation. Its peak value here, 9.2 volts. So even with a gain of 1, we are seeing 9.2 volts, but compare that to the proportional controller where it was wanting 10, 50, 100 volts, depending on what the gain was. This is going to be a peak value, at least, much smaller. And finally, we're seeing we do have an overshoot since it is an underdamped system here. So we do have a higher voltage at peak than what we want at steady state. So it goes up to 6.7 volts. But we can impact what that peak voltage is going to be, or what the overshoot is, by choosing different gains, because the max overshoot is determined by the damping ratio, and the damping ratio for this closed loop system is going to be determined by the gain we choose. All right, so let's just change the gain. Let's look at what if our gain is 5. All right, we see the natural frequency is now 1.41. We see the damping ratio is now lower, 0.14. And we see the peak time is about less than half as much as it was before, 2.2 seconds. And then graphically we can see what's happening. So the response time is much quicker when we increase the gain to 2. We're getting to our peak value faster. We're getting to our steady state value also faster. And as we know from the final value theorem, the final value didn't depend in this case on what the gain was. We're still getting to a steady state value of 5 volts. However, with a gain of 2, a drawback of that was that our peak voltage is now about almost 19 volts in order to achieve this. But we got a smaller peak time, and we also see here that we have our overshoot here, it goes up to about 8 volts. And finally, for comparison purposes, let's look at what if the gain were 25. We see the natural frequency has increased, the damping ratio is even smaller, 0.06, and the peak time is about 1 second in this case. And on the output graph, all of that is reflected. Actually, our overshoot is a little bit higher. It goes up to 9 volts now. But now, as we again increase this gain, the peak input voltage we need is now up to 40 volts. So at some point, it's going to become impractical to put such a high peak voltage into our system, even if it's getting closer to the response we want. One way to remedy this will be to use a different controller, like we're going to talk about in subsequent lectures, or get different equipment that might be able to handle these higher voltages. So let's look at them all compared at once, like we did previously. So if we look at these 3 candidate designs, these 3 candidates for the gains all at the same time, the 1, the 5, the 25. Again, I'm picking these just for demonstration purposes. We could pick any positive gain, and we can see what the effect is on the system. But let's first look at the lower, the output voltage. So as we increase the gain from 1 to 5 to 25, the black to red to green, we see that peak time is going down, but we also see that the max overshoot is going up as we increase the voltage. So if we want a quick response, it is getting quicker, however, at the cost of a higher overshoot. And we also see that the other cost is the higher peak input voltage that it's going to take between the 1, the 5, and the 25 gain. And that trend, if we saw anything in between the 1 and the 25, it's going to still hold true. And the last thing to look at on this comparison is, again, after 30 seconds, the output voltage for all 3 of these gains, and again, any positive gain that we choose, is going to go to 5. And again, we know that from final value theorem. One note is the final value theorem is predicated on having a stable system. There will be there could be gains we select that actually make the system unstable. So we do want to check under what conditions, under what gains the system is stable. Because even though it looks like everything works out in the math, if we violate one of those, the requirement of having all of our poles in the left half plane, and then are applying final value theorem, that's not a valid use of the final value theorem. So we do want to double check that, what gains are not going to be allowed. One more specific gain to look at, if we look at the poles here, if I choose Ki to be 0.1, I'm going to get 1 minus 1 is 0 on top, and I'm going to get here repeated poles. So let's just take repeated poles is going to mean we have a critically damped system. And same thing if we look at the zeta value, if I put 0.1 in for Ki, well, I get 1 over 1 is 1, and a zeta of 1, same thing, it indicates we have a critically damped system. So going back here, let's put in 0.1 for our gain. And we see it's not underdamped, so the natural frequency doesn't really make sense. We don't have a peak time because it's critically damped. And we see its trajectory, it's asymptotically from below, approaching that 5 volts. It is still stable, it still has a steady state value of 5, but we don't have those oscillations. This is a gain we could choose if this is how we wanted the system to respond. But like I said before, we generally like underdamped systems in our control systems where we're able to modify them to get a much quicker response than we can get if it's critically damped or especially if it's overdamped. So finally, a summary of applying the integral control and specifically to this plant. For this system, we showed with final value theorem that any positive gain we chose would drive the error to 0, would drive the steady state value of our output to 5 volts. Again, not universally true. For a different plant, an integral controller might not do that. We might be stuck with the steady state output having a K in it, like we saw in this plant, the proportional controller. But for this particular plant, yes, it did work, and we want to show that for any new plant that we encounter, will our controller drive steady state error to 0? We saw that if we change what the gain was, we looked at 0.1 through 25 really in this example, the system is going to behave differently. When it was underdamped, as long as it's underdamped, the peak time was shifting, it was getting smaller with increased gain. However, the overshoot was getting larger because we were playing with what the damping ratio of the closed loop system was, what the natural frequency was of the closed loop system. But again, all of them eventually did get to 5 volts, but how long it took was different from system to system, from gain to gain. And we saw that for implementing the integral controller here, we went from having a first order open loop system to now having a second order closed loop system. And that's why we are now in this closed loop feedback system seeing oscillations, even though the plant itself originally wouldn't have oscillated. This closed loop system that we're creating does. So we're introducing these oscillations, we're introducing having overshoot into our system now. So we've only looked at through simulation how is the system's response being affected. So next we're going to look at a little bit more systematic way that we can assess how quickly our system is going to come to steady state. How can we assess what gain should we choose to get the desired response?